Okay, let's get started. So, good morning, good afternoon, or good evening, everyone, depending on where in the world you're connecting to this webinar. Thank you very much for joining. Today is a second webinar of a webinar series, what we are doing about innovations in battery management system testing. Today's topic is choosing the optimal battery cell emulation technology for a battery management system HIL testing. For the ones who don't know us yet, a quick introduction to OPAL-RT. We are a Canadian-based company with a bit over 400 employees and over 25 years around, always in the area of hardware-in-the-loop simulation testing. We come predominantly from the power systems market and power electronics market, and with the electrification of the mobility market, of automotive market, we strive strongly also in that direction. And our advantages, what we have, or our knowledge, what we have with fast phenomena simulation, can be used in that area, or can be very beneficial in that area as well. We are a very innovative company and reinvesting some 20 to 30% of our revenue each year into R&D, and try to be at the forefront of technology together with our users, of course. To give you this webinar is together with one of our principal partners, or our principal partner actually, for battery management system testing, comemso. So Anita is joining us as well as the main presenter. So Anita, maybe you introduce yourself quickly.
Yes, hello. My name is Anita Athanasas. I'm the co-founder of comemso. My husband and me, we have founded comemso. Previously, I have studied technical informatics. And yeah, I'm very happy to be able to present this to you, because we're doing that topic quite for a long time. So the battery cell emulator, or the BMS testing topic, is one of the main cores at comemso company since 2010, 2011. So yeah.
And this is actually also the reason why we are partnering with comemso, because the comemso is at the forefront of this cell simulation, respectively emulation technology. And Anita will tell you more about it. Quick introduction to myself. My name is Timo. I'm go-to-market director, respectively. You could call it also strategic product manager at OPAL-RT for the power electronics and e-mobility sector. When talking about e-mobility, here's a quick overview on which applications we as OPAL-RT serve for the e-mobility. As I said quickly before, our focus or our strength comes from the electrical world. That's why also for the automotive testing applications, we've pretty much focused on the electrical applications. And this is, of course, in an electric car, for example, the charging system, charging onboard charger, the battery, and the inverter and motor ECU, of course, with other power distribution units. This were the applications, and of course, when looking at the testing methods, what we focus on, I said already, we are predominantly working in hardware-in-the-loop simulation. Of course, with the same systems, you can do model-in-the-loop or software-in-the-loop, and extend also to power level hardware-in-the-loop testing. And when you, let's say, look at all the different testing methods and testing approaches you have, Then from left to right, you have a more simulation and model-based approach to the right, where it's more a real-world and pure physical testing approach. And of course, the flexibility is larger in the simulation world, and it gets more and more realistic the more you get to physical testing. And at that level, I think all steps are beneficial. However, the earlier you can start testing, the earlier you can find errors, of course, in your control algorithms, then the more money you save at the end for either more extensive testing or maybe tests you maybe have not covered. So our recommendation is clearly to shift towards simulation, however, with a good amount of being realism, so being very realistic. So we see the sweet spots in the software hardware in the loop and power hardware in the loop testing. Good. So recapping from our first part of the webinar, 3 weeks ago, we've talked about or had interviews about the trends in battery technology, and just to recap a little bit on how does it affect BMS testing today. So the trends we've clearly seen is of course higher energy density in the battery and fast charging capabilities. These two are of course not very surprising because these are main topics in order to assure acceptance by the end users of a battery electric car, because range anxiety is still a big topic and nobody wants to wait an hour at a truck stop to get the car charged and things like this. So these are of course key. Battery safety is still key, even if it's not always prominent, but this is the underlying basis of course all developments to make sure that we are in a safe environment and safe application. More and more we see integration of solid state batteries, of course, in order to get higher energy density done. And more recently comes also the focus on sustainability and recycling. It's not surprising, however, was not the principal focus in the beginning, but definitely now after many years and over a decade of electric vehicles, this is coming more into focus. And the BMS needs to be adapt to it, to be more modular, easier to assemble, disassemble, maybe wireless in future, and of course, fast and easy to repair. So finally, a little bit of overview from our side on what we cover in terms of BMS HIL testing solutions. Together with comemso, our partner, we provide cell emulation, so basically sync and source systems on the cell level. Then it comes all the way through to the pack level with full pack emulation, what you see at 0.4. Of course, full pack emulation then meaning, for example, 800 volts and various hundreds of kilowatts. And as you don't want to deal with all the safety requirements for this testing, maybe always there's also hybrid simulation approaches, especially, for example, sync and source system at the full voltage level, for, let's say 800 volts, but just at milliampere ranges if you want to check for isolation checks, respectively voltage related checks. And there's a third topic, which is a virtualization topic, which will be the topic of the next webinar in 3 weeks, which is the virtualization of chipsets. So when we have the BMS as a master BMS, we have the cell monitoring devices, cell sensor electronics, or CSC, CSEs, and so on, how they called. And for depending on different test strategies, you might want to manipulate these as well. So we also have solutions to virtualize these, but definitely want to underline all four different test solutions cover different test requirements. So probably in the full BMS testing world, you would need to consider a combination of all of these in order to cover fully. Yeah, and of course, with our HIL approach, we can cover all of these different test sets with the same battery models on our HIL system in the background. That's so far from my side, a short introduction on the overview of our offerings. And now I would hand over to Anita in order to that she can explain more the specialties, requirements, and challenges also on testing, on battery testing on cell level with the cell emulator.
Okay, thank you, Timo. Then I switch to the presentation.
Yes.
Okay, can you see?
Yes.
So the challenges on the one side, you have to do the development. On the other side, you have to consider what do I need to test. So BMS, testing BMS is a big challenge, a lot of things to consider, and this should help you to consider all the points and different views, what else needs to be covered with testing, okay? And how can I do this? And yeah, so then table of content, quite simple. What is a battery management system? The test requirements of a BMS and how to realize. So you see simple picture of a BMS. So this is the typical thinking, okay, we have battery cells, we have a ECU, and it has to manage everything. But there's more in the background. So we have the battery management unit, which is kind of the brain, with the algorithms and collecting all the data and making all the analysis and the big judgments. And then there are also the cell monitoring units, also cell management controllers. So there are different names for this. Like, you can call it like short CMC. And they look on a set of cells and manage them, and also the temperature of this, and also for the management of these cells, there are different possibilities. So they need to be monitored, and then, for example, to be done with passive or active balancing. So all the cells have to be kept in a similar level to be able to do some the right algorithm. So you can only charge the cells to the 100% if all the cells can go to 100%. So when one is higher than all the others, you cannot go and charge all at the same with the same pack voltage. So therefore, these algorithms are important. So my job is not today to explain all the details how to develop a BMS, but these information are just like basics what need to be considered, okay? And for this, the CMC and the BMS have to do different jobs. For example, they need to do the cell voltage monitoring, and for protection and safety management, it needs to be ensured that there's no overcharge, no deep discharge. So there's also load management. It needs to check also the standby current, the low cell voltage, and so on. And also for increasing the lifetime. So the general management and the calculations. So you need to do like the cell balancing, passive or active, depending on what you want to do. The passive balancing is the cheap procedure, but not that effective. The active balancing is more the expensive, but you have more efficient use of the energy. Okay, and also for the active balancing, there are different methodologies and different kind of possibilities. So, but this is not a topic today. Okay, we want to know just how to test it. Okay, so therefore the cell balancing itself and also the state of charge calculation on cell level, but this concludes also to the pack level. Okay, and the requirement for the cell monitoring, the big challenge is that we have the low or the flat curve in the range between 20 to 80% of the state of charge. So here, sure, it depends also a little bit on the chemistry, but generally this is the typical behavior that we have, very low range. This means we have also to measure with a high accuracy. So the BMS has to measure with a high accuracy, for example, with accuracy of plus minus 1 millivolts. And for a test system, so this means even higher challenges. Okay, so it needs to measure with the and to get also the values with a low ripple. And yeah, the challenges for the test systems are related to this. So fast control to behave like a battery, and high isolation, more than 1 kilovolts, even more. It's going to 2 kilovolts because of the summary of the cells. Now we are in the range with the high power charging of about 1500 volt, 1600 volts for the Asian, for the charge, for example. And for the megawatt charging, it's also going into 1500 volts. So now this is not only theory, so it's already in progress for the development. Okay, and yeah, also the voltage drops over the cable. So this is also a challenge for the test bench. Let me explain why. So this is generally, we simulate the cells for the BMS that we can measure them. But when we put this in a testing setup, we have a difference between the real pack and with the real cells, because you see on the right side, the example, when it's finally packed. So you have all the cells, you have, for example, smaller than 30 centimeters, the measurement wires between your real cells and the electronic device, the CMCs. When you have a test system, so the size gets quite bigger. So it's not only your setup with the DUT, the device under test, with different PCB variants, for example, but it's also the test setup with the battery cell emulator. Okay, so then we're going into the direction of 2, 3, or even more meters. And this creates different cable length. So that's already a difference between the real setup and the test setup. Okay, and this test setup creates the problem that we have the Ohm's law. So we have physics that we have to consider. With the cable, we have a resistor. With the connectors, we have a resistor. So every small resistor in between, we get a voltage drop. Yeah. So when we want, for example, to make balancing with 1 amp, this means according to Ohm's law. So let's calculate with 1 ohm. This makes it a little bit more easy. So when we set 3 volts, we have 1 ohm, which the BMS draws. Then the BMS will see 2 volts. So from 3 volt to 2 volt, 1 volt drop. In reality, it's not 1 ohm, it's about a half ohm. So but it depends also on your thickness of the cable, how good are the contacts between the connectors. But roughly, so it's even high enough, isn't it? So when we consider, we have the need of 1 millivolt accuracy that the BMS has to be able to measure in the meantime. Okay, so and the test system has to provide the exact values. So, and therefore it shouldn't be that situation that your BMS is different values that you want to provide during the testing. So therefore we need a test system which is able to execute very accurate that values that you are also setting as your command that should be provided. Okay, and that's what we do. So when you say 3 volts, that's exactly what you have to do. So it makes a difference when you read also technical data sheets. So to set the accuracy and to set the voltage ranges and so on. So this is like on paper, but what is on the reality? Is it at the output of the test system, or is it really at the input of your device and the test? So these are the slide things which you have also to think and to consider when you're selecting a test system. Okay. So when we're looking now at the passive and active balancing, so when we have the passive balancing, you discharge with a resistor the different cells on the level of the lowest cell, and then you can charge them again. And with the active, you try to get the voltage which is too much at the one cells and put it in the lowest cell, for example. There are like different possibilities with switching or inductive switching between the cells. Capacitive are also possibilities, matrix and so on. So a lot of things have been already tried and made. This is so another topic. So a lot of different solutions are already evaluated and provided on the market. But how to test this? So when you go to active balancing now, you want also to charge. And then this means the current goes into the other direction. So we're simulating at the once you discharge a cell, at the other you want to charge a cell. And here this is also a challenge or an important topic, that the switching is possible without any switching. So that what we use is the physics here again. So the Kirchhoff law supports us that we don't need to switch between source and sink. The dominant value, so when you have a higher voltage on your cell that you want to sink into another one, then the dominant voltage is that one that provides also the current. So this is what we can see according to this Kirchhoff's law as a benefit. Okay, and here there's also wide range of the load, so we can go up to about 5 amps to make these active charge and discharge possibilities. Yeah, and when you want to verify this charge and discharge processes of the cells, it's also important to know how much energy was flowing out of the cells or into the cells. And you have the on the one side the measurements, but a lot of cells and all these in parallel working. So therefore here a Coulomb counting is helpful to get you a kind of integral measurement over the time. Okay, so therefore this could be also an interesting point for you to consider for your test bench. Okay, it helps, for example, to avoid too fast and irregular charging or discharging of the cells. You know, this could be also some disadvantages for the health of the cells, and avoiding just too little balancing of the cells, so that you get really on the value that you want. So yeah, and for this, with the Coulomb counting, you can also get this calculated over time. And so this is everything made in the background of the electronics and provided you then cycling the values. Okay. Also very interesting to have this on every cell, that it's not only on one cell, so you can really see the behaviors also between of them. Okay, then the topic deep discharge is also interesting. So when you consider, for example, the typical application is motorbike, you put this into the garage for the winter, and it maybe wasn't completely full, or even if it was, or if your BMS is not going correct down to sleep or is still discharging the battery, then this will be at the end critical. So you can really deep discharge your battery, and so I think motorbikes is a typical application, but nevertheless also with cars. So it you make a big trip, go to big holiday over many months, I don't know, so maybe a road trip or something like that, and after that your BMS has discharged your battery. So, and this is a big damage, so therefore to avoid and this kind of damage of the cell, this is means a complete replacement. Therefore, it's also important to check the leakage current of every cell and to make these current measurements. So the current measurement on the one side and the leakage measurement on the other side. And having an automatic range selecting is also very nice convenience here. Okay, so these parameters should be also calibratable. The source, the voltage, the sink, and all the current and Coulomb counter measurements. Okay, and this for every cell and on each separate. Typically, you might do this once a year. It depends on your testing requirements, on your validation. If you use such a test setup, not only for the development validation, like at your V testing process, but also for the production line. So this is even a more important topic. Okay, so therefore possibility to make the validation of the accuracy and also in general the calibration is an important thing. Then let's have a look on the electrical fault simulation, like to check extended cabling failure, on short circuit possibility, and safety management on cabling failure. Okay, and why I'm thinking also about this as a system. So when you have this as a separate failure injection box, this will create other difficulties. On the one side, you have additional the cabling to put this in between and so on, makes it more complex. And on the other side, you remember we have this high accuracy requirement. Every connection in between creates an inaccuracy when you're doing the balancing, or the general, when any kind of current is flowing through the cells, you have a voltage drop, you will not have again the accuracy. And to have a system which includes also the fault injection as a system which is like designed as one unit, then you have the benefit that you will have also the possibility to get a higher accuracy, like that this additional fault injection is integrated and avoiding that you will lose your accuracy topic. Okay, and therefore this is also important what we do. And here, for example, you should be able to add the single cells into the stack. Gives you the possibility, for example, to simulate also like connecting the BMS in different orders of the cells, or to break out one cell or break the stack. The next possibility is to create a short circuit. This is like what happens when over time you get some dirt inside, or yeah, any kind of connection between the cells. And also a polarity change could be, for example, a mistake in the cable or in the production. And then the question is what happens, how the BMS can handle this. Yeah, and is it recognizing that mistake and things like that. Okay, so therefore this is a possibility of the fault injection. Then when we look at the whole setup, so this means we have the high precision battery cell emulation included, we have the connection to the BMS itself, and we have the extended failure simulation. This is something even more. So with the inside the battery cell simulation, for example, we have already integrated this fault injection, but a second step of fault injection is the let me show you that you not only break the cell itself or break the cell cascading, but you also break the measurement wire between your cell stack and your BMS. So this is the measurement wire itself of the BMS. Okay, this is the extended failure simulation. So in summary, we have then 4 electrical fault injections on this kind of possibilities. Temperature, very interesting topic. So we have the temperature sensors in the BMS. Also here is the challenge. These temperature sensors are potentially in this high voltage area, and it's important to see the temperature of the pack and the module to be able that your BMS is able to monitor that, to protect over temperature of the cells, and also to make kind of thermal management. For example, when you have winter, to heat up your cells that they are working in the best conditions to have the increasing lifetime and high capacity also over a long duration. And yeah, so therefore this virtual battery needs to be also simulated then as cold battery or hot battery, and that the BMS is able to recognize that. And therefore what we use here, so emulation of the temperature sensors, NTC or PTC, and these are also galvanically isolated for this high voltage application. Okay. Another topic, isolation test. So this is not only a monitoring or measurement thing, it's also a safety topic. So when you consider your battery in the EV is not allowed to be connected to the earth ground, to the protective earth, for example. The reason is if you have the battery itself and it's like free of potential, so you have just the battery like you in your hands, so nothing happens. You can put on one pole, nothing happens. But as far as you have one pole connected to the earth ground and you touch the other pole, then you get a electrical circuit over the ground with your feet, and then we have the danger. And because of this high voltage area, this is a very critical thing. And therefore, you have in your BMS an isolation monitoring device, which observes DC plus to earth ground and DC minus to earth ground. Okay, and it is not the fastest process, so this can take a couple of seconds, and therefore this is the isolation itself is the important thing. Yes, several different safety topics more, so you shouldn't be able to touch one pole directly, for example. Therefore, you have also at the EV inlet the isolated contacts and so on. And so, but in the next, like, the most critical thing happen when multiple things go wrong. So, and therefore you have here a couple of seconds where the isolation monitoring and the reaction should act. Okay. What we can do here is we can simulate the isolation fault to decrease the isolation resistor between DC plus to earth ground, DC minus to earth ground, and we also measure the potential between DC plus and earth ground and minus and earth ground without influencing this isolation. So this is generally an opposite by itself, because these measurement methodologies have influence to each other. So, but this is what we also worked to be able to provide that possibility. So you can verify then also the values with this measurement and not just changing any values. And then, so this feedback possibility is also very important with the testing. So testing or test systems have always the requirement to give you a transparency, that you're able to double check the values that you're setting, and you need to the possibility always to get the verification, is that value set. So, and this is not only for the isolation fault, but also for the battery voltage, cell voltage that you simulate, and all these electric faults and so on. So this is another thing which a good test system does. So it provides the to the tester itself the verification possibility to know, okay, I have set this and I get this also. Only then you know that your test result is valid. Okay. Pack voltage is also an interesting topic. So pack voltage is something that the BMS is also monitoring. So the battery management unit itself. And what it does, for example, it verifies the pack voltage with the summary of the cell voltages and compares if the value is the same, if it makes sense. So this is additional verification thing that you should also do with your testing, and therefore also having a pack voltage emulation is interesting. So you could do, for example, if you want to keep it simple, you just take the cascaded cells and take the lowest minus and the highest plus. But then you don't have the testing possibility to create also here a discrepancy. So this is a very interesting test case also, to have a separate power supply and to simulate another pack voltage than the summary of the cells, and check what is the tolerance which your BMS accepts, or when it does it say, okay, there's something wrong, I have to give an alert. Okay, so the power supplies, this is not the main topic what comemso does, but we can also support or integrate, or so that's something depends also on the specification you need. Then generally the charge current, discharge current, and overcurrent topic. Okay, so we are also talking here about the pack current. So when you really when you're testing, when the BMS observes that the charging is made, okay, so you have these 100, 200, 300, up to 500 amps that you want to see how your BMS is behaving on that, combined with all your other algorithms. And so having these currents is not that convenient to have this on in your lab. So how can you avoid to reduce this safety risk with your test setup? Now, the most convenient thing is, for example, to remove your shunt of your PCBs and to emulate the shunt also with the hardware in the loop system. Okay, so that could be a possibility if you say, okay, this is another option, or maybe you have a current sensor inside. So also current sensor emulation is possible. Okay, you can also go with the 500 amp with the power supply, for example. So if you need this also, here we have smart solutions, but it is not that low. Yeah, the risk is a little bit is higher. You have to do more safety for your lab when you're going with these values for testing. Then, okay, state of charge. And now, based on that, also the state of health calculation and the history. So it's kind of a logbook function to count the cycles, min and max values, and based on that, also use this for your calculations. Okay, so to do that, it is helpful to have a battery model. So all the tests before we could do with static values. So like set the cell voltage, which is like creating a over voltage alert on your BMS, or a over temperature or isolation fault, and make this even in different combinations. Yeah, so that is really the interesting, the funny things to test. But now when we go on the next level and do this even with dynamic behavior, so we go with the battery model. And here, this is also something which we very appreciate to work with OPAL-RT to complete this with the real-time calculation on OPAL-RT's real-time PC, and with MATLAB Simulink battery models, and to control this also in the test automation. Okay, so then this is a very nice, powerful combination then for the customers. So now, yeah, that's it. I think isn't quite complicated, right? If you need help also to get the setup or how to test, and also we have on OPAL-RT side and on comemso side very experienced engineers which create then the related system configurations. Okay, and on the one side you have then the complete HIL system, and you see we do this quite for a long time, and so with the best values on also technical values, and a very broad experience with customers all over the world, really from California to Japan, Europe, everything is quite inside. We're very proud on this. You can hear this, and then you can also get different system sizes, different system configurations and customizations depending on what you need, and also in combination with OPAL-RT, even more powerful benefits. Thank you very much.
Good. Thank you very much, Anita. This was very insightful, and I'm also very happy to learn from your expertise and your company's expertise in terms of cell testing. I learned again something new. So I just wanted to check, of course, the floor is open for questions. So far, I don't see a question in the chat, but of course, also sometimes formulating questions might need some time for the one or the other to think about it, but don't hesitate to put in your questions. It can be anonymous as well. In the meantime, I would have a question to you, Anita. And you mentioned that the voltage, voltage measurement is very important because in order to build up the state of a charge value correctly. And on the other side, you also mentioned that of course, the test system has different wire lengths and has a different lengths than the real system. So how are you actually making sure that for the test in the test system, you have the right value, the right voltage value provided to the BMS. So what is the key here?
Okay, so there are two things to consider. On the one side, when you have the requirement of accurate that your BMS has to measure with an accuracy of plus minus 1 millivolt, then the BMS has also how it measures. It makes a sampling, and according to the sampling theorem, it means that your simulator has to provide double better accuracy. So, and what we do is we go even one step further, and we make accuracy up to plus minus 250 microvolts where we calibrate. That's the one thing. The other thing is you have the wires. And so we talked about it has these 30 centimeters, for example, what you have between your real BMS and the real cells. So this is also the range where we recommend and say, okay, we make the harness accordingly and we compensate the voltage drop over the harness. So we have a special control design inside that you have the compensation of the voltage drop, and then we generate the accuracy at the input of your BMS setup. So also here you have a little bit some wires. So but then it comes close to the reality how the BMS really measures the accuracy.
Okay, so you have a compensation methodology basically in order to provide a little bit a higher voltage, which is
Exactly.
yeah. Okay, good. And now we have a question in the chat. I will quickly read it. For the CAN communication between the BCS, so the cell simulator, and the BMS, does the BCS offer a set of parameters which the BMS side adapts to, or does the BCS adapt its parameters to accommodate to what different BMS might write? I'm not sure to fully understand the question, I have to admit. I'm not sure, Anita, if you have a better...
I think I got it. So these are things then of your testing software. So because on the one side, you have to create test cases. You need we have customers which have their preferred test chains, for example, that they say, okay, I need to do some test cases, and how they program the test cases. So this can be decided by the customer or can be helped by OPAL-RT. And inside the test case, you have on the one side then the communication to the BMS, checking the values, and the communication to the battery cell emulator, and setting the values, get the measurements back, and then you compare what is your BMS doing and what is the BCS doing. Is the BMS following your test control? If yes, does the BMS react correctly? If yes, then you have a pass. Okay, so therefore, this chain is made by your test case or your test software.
So, okay, in terms of test automation, yes, we definitely provide the possibilities of respective test automation, and yeah, there can be the respective standard, for example, DBC files input for the CAN communication verification.
Mm-hmm.
Okay, next question. Which battery capacity ranges can be simulated? Yeah, okay, so can they be fully configurable? So basically it comes to what are the voltage and current levels we probably provide.
Yes, so the voltage and current levels are, so we are close to 0 to up to 8 volts that we can emulate per cell. And we have different variants depending on the customer selection, but like up to 6 amps in the source, and I think it's about 5 amp in the sink. And so with these parameters, you can set the electrical behavior. The capacitance is then a model thing. So this is like what you select on the model. So this means when the cell emulator measures that there's a discharge, you get this current into your battery model. And the battery model calculates, okay, there is a discharge of the cell, and depending on my capacitance of the cell, which you have in the model configured, it discharges fast or slow. And depending on that, it creates then a calculation, okay, which voltage level do we get at the end? And this is the parameter that you set then to the battery cell simulator, and then the battery cell simulator should exactly execute that value. And here again, the point is very important. The best battery model doesn't bring you a value if your hardware is not able to execute this accurate.
And it also shows the importance of the measurements, because the measurement input is, of course, also important for the right model calculation, and vice versa. Mm-hmm. Okay, just because to make sure, of course, we're talking about the cell level here. So we're not talking about the full pack level, because this, yeah. I guess this question was in that direction. Good. So far, I don't see further questions, but actually, I would have a one following this last question. Is you mentioned like 6 current, 6 amps, 5 amps sink and source capacity. Do you see requirements for higher currents in the upcoming future? Do you have requests also for higher voltages? I haven't seen that much, but maybe for higher currents. Yeah, what is your projection there?
What we see is the increase of the amount of cells due to the charging technologies. So we're in both areas working on the charging topics, because we have also the test systems for testing electric vehicle charging protocols and charging behavior, and also the charging station with the charging interface. Okay, so and there we see how the standards change, what are the new values, and in which direction is it going, what's happening in Japan, what's happening in China, what's happening in Europe and US in these standardizations. This is very interesting. And so when you combine this information, you see it's going into the area of megawatt charging. Now the range is going to 1500 volts, 1600 volts in the pack voltage. This means more the amount of or the number of cells is increasing. About 200 cells is getting the new normal. And on the other side, the charging current increases also, but this is not influencing the balancing current itself. It's the charging current. Okay, for the balancing, the algorithms keep quite the same. We have sometimes higher requirements, but this is a very rare number what we have here. So it's like, you know, it's like in statistics, you have this kind of Gauss, so you have on different corners, you have some special requirements sometimes, but these are special applications. For automotive, I would say right now these values of about 5 amps charge and discharge current per cell is state of the art, and this is what is very common and often used.
Okay, perfect. Thank you very much, Anita. I don't see further questions in the chat. Thank you very much also to the audience for participating. I hope it was insightful. For me, definitely was. As I said, I always learn from you guys, and I'm very glad to work together with you.
Same to you.
If you also appreciated this webinar, we have a quick poll after the webinar. We would really appreciate to get your feedback in order to keep on improving our offering. Good. So without further ado, thank you very much. And that's it from our side. Sorry, last hint, of course, as we said, this is a webinar series. So in 3 weeks' time, on the 27th of June, actually, we have our last part of this webinar, which will be about innovation. Which will be about the game changer in BMS HIL testing, FPGA software technology. So it's predominantly about the cell monitoring device system testing, or cell monitoring device virtualization. Good. Thank you very much and have a good day.
Thank you.
Bye-bye.
Bye-bye.